Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We're at lecture 7.3 and we're beginning to look at OpenCL host code. The objective of this lecture is for you to learn how to write a OpenCL host code. And we're going to show you how to create an OpenCL context and how you can create work queues for task parallelism and submit all kinds of activities such as data copies in and out of the device and launching kernels and so on. And we'll show how you can use device memory allocation and how you can do kernel compilation at runtime, and then kernel launch at runtime, and host device data copy. In order to understand the OpenCL host code, we need to first introduce OpenCL context. The OpenCL context, as we mentioned in the previous lecture, it contains one or more devices, and the OpenCL memory objects are associated with a context, not a specific device. This is very important to remember because it's a source of a problem for quite a few OpenCL programs. And the API function to allow you to create a memory buffer or to create or allocate memory in the device is called CL create buffer. And whenever you call this API function, you will be creating a data object in the OpenCL context. And if there is an error that will be raised if the allocation is too large for any of the devices in the context. Remember, a OpenCL context could contain multiple OpenCL devices. So if we have OpenCL devices that has smaller memory than others, whenever we create a buffer or allocate a piece of memory in the OpenCL context, the space will be reserved for every device in the context. So if the memory object is too big for even the smallest device in the context, then we will actually have an error. And so we need to pay attention to this situation. And each device needs its own work queue or queues. And now we'll see how we can use these queues. And it's very similar to the CUDA stream queues. Memory copy transfers are associated with a command queue, and thus every memory copy operation is associated with a specific device. So here we show the OpenCL context setup code, and it's quite simplified. For those of you who are interested in writing OpenCL code in a more extensive basis, I would like to refer you to the OpenCL programming guide and OpenCL standard specification. So here we show that we have a data type called CL int, and this is just an integer type in OpenCL that you can use to contain any error message returned from the OpenCL command. So we will use CL success as the default in these variables, and whenever there is a error, then the function will actually return a failure error code into the one of the parameters. And then here we show the API function for creating an OpenCL context. And the context is actually going to be used with a handle, and the handles, all the context handles should be declared as CL underscore context type. And here we're declaring a handle called CL CTX, and this is just an arbitrary name. And this variable is going to hold the handle through which we can access the context in the OpenCL program. So here we call the CL create context from type. And we were going to specify the type of devices in the system that we would like to include in the context. And here we showed some of the parameters, and it's quite involved. If you really want to understand all the parameters, you should really go to look at the OpenCL programming guide. But here we show some important parts. We show CL device type all. That means that we're going to collect all the OpenCL devices in the system into this context that we're creating. And then we're going to, the last parameter is that error flag variable. So we pass the address of the variable into the function, so that if the function encounters any error, it would actually return the error type into that parameter. So then we have a sequence of activities so that we can actually get enough information and create a command queue for the particular device that we would like to use. So to understand this code sequence, we need to understand that we're going to have multiple vendors, and each vendor is going to implement these API functions in different ways. So it turns out that there are also different kinds of contexts that you can create, and therefore there's some real flexibility in terms of the amount of information that would be associated with each context for each vendor's implementation. And so we're going to need to have a sequence of code that allows this piece of code to work with a wide range of implementation and devices in the OpenCL system. So here we show a size that underscore T type, which is essentially an integer that will contain the size of some memory objects. So we declare a variable parameter size, PARMSZ. This is, again, an arbitrary name. You can use any name you want as long as you use it consistently, declare and use consistently. And so we're going to call CL get context info. So this is how we're going to be able to get the size of the parameter. We would first inquire into the OpenCL runtime and say, how much space do I need to reserve in order to be able to receive all the information you're going to return to me in my real query. So whenever we pass that pointer to a size parameter, then the get context info will not give us the actual information of the context, but it will actually just say, you need to allocate so many bytes in order to be able to receive all the information I will give you when you do the next query. So so after this function call, the variable parms parameter size parms.sz will contain the number of bytes that the program needs to allocate in order to accommodate all the information to be returned from CL get context info later. So that's why we use this parm size variable to do a memory allocation. And the allocated memory is going to be placed into CL def s. So this is really just the information for all the OpenCL devices that we have in that context. So the OpenCL specifies a type called CL underscore device underscore ID pointer. So CL device is actually going to be an array that will every element is going to be a ID that we can use to access one of the devices in the system. So now that we have enough memory, we can call CL get context information again. And this time we just pass a null pointer because we already know the size. So we use the parm size to actually tell the context information that I can receive all the information you're going to give me. So the CL depth is going to contain that array is actually going to contain all the pointers that we're going to be getting. So this CL get context information is going to take that freshly allocated array of pointers to the devices or IDs to the devices and ask the get context info to fill in the IDs and information for all the devices in that context. So once we have called this, we have the device information available, the devices in the system. So here you show an example where we can create a command queue for one of the OpenCL devices in the system. In general, you will need to be just like the CUDA device query, you need to go through all the devices in the system in order to be able to figure out which device you want to use. But here, for simplicity, we just show that we just assume that we're going to use device 0. So we're going to call CL create command queue with the context handle and with the device ID. So we're going to just use the 0th device in the system, and then we're going to pass the address of the error variable, so that if there's anything that goes wrong in creating this command queue, we can check the error that's returned in that parameter. So again, I would like to encourage you, for those of you who want to write more OpenCL programs in the future, go into the OpenCL programming guide to and look at more details about these parameters. So as it turns out that OpenCL kernels are compiled at runtime by default, unlike CUDA, where the kernels are in general compiled at when you prepare the kernel, you will do the compilation as you are doing with web GPU so far with all the MPs. But in OpenCL, the kernels are actually not compiled until runtime unless you specifically tell it to prepare the kernel for execution at compile time. So we're going to prepare the kernel as a string. So we're going to declare the kernel as a big string variable. So here we see that we have a string that starts with double quote, and it's going to contain that simple vector addition kernel. And this is the kernel that you will be developing for this optional NP. And then, so the entire kernel as a string will be assigned to a string pointer. We'll call it vect source and vector addition source, VADD-SRC. And this is just declared as a constant, string pointer or character pointer. So once we assigned a pointer to the string, then we can give this program or kernel into the runtime compilation API. So here we declare a CL underscore program. So this is a pointer to the actual compiled kernel program that the API function will be generating. So we call the CL create program with source, and we give it the context information, pointer to the context, and we're going to set the flag to 1 here, but you should look at the details of this API function to see what other options you can have. And we're going to be passing the string, which is that the source code of that kernel, into the create program with source. And then we're going to have use the null pointer here and then the error flag. So essentially, we're handing the source code into the CUDA to the OpenCL runtime, but it's not compiled yet. It's just there, and then it's prepared for compilation. And you can access that. You can tell the system to compile the program by handing the CL PGM pointer. Now it's pointing to whatever is being prepared in the runtime. And then we can prepare compile flags. For all those of you who have used C compilers and so on, you know that there are many compiler flags that you can use. So the compile flags are going to be created using a string. So here is a simple example. We can just print the -CL, -MAD, -enable. So essentially, we're going to have multiply add enabled in the compilation. So there could be many other flags that we can use. So we assign, essentially we print the compile flag as a string into this variable called CL compile flags that we just declare here. And you need to declare that string array to be big enough to contain the longest compile string flag that you would like to enumerate in your string. So then once you have the compile flags prepared, then I can actually call an API function to really do the compilation. And this is called CL build program function. And it will be taking that pointer to the source code that you have deposited into the system, and then you would set some of these parameters, including the compile flag pointer. And we're going to be using Z and nulls for all these other parameters, but you definitely should look at the details of these parameters from the OpenCL programming guide. So after this API function, we actually have the code that is compiled. However, once we compiled, we need to generate a kernel, a executable kernel that we can call at runtime. So this is done by a CL create kernel API function, where we take the program that we just prepared, and then we will name that kernel DADD, and so that in the future we will be able to just invoke the kernel. We can refer to this kernel with that name, and then there's an error parameter that will tell us whether anything went wrong when we create that kernel. So once the create kernel function returns, we have a usable kernel and we create a pointer called CL current. This is just an arbitrary name that we just happen to pick for this example, but we can use this pointer to launch kernels in the future. So all these pointers to kernels must be declared as CL_kernel type in OpenCL. As you can see, it is a fairly involved process just to be able to prepare a kernel function that we can call later on for execution. So now that we understand how to compile and create a kernel function, we can begin to look at how we can allocate device memory from the host code. So we have, in general, we can use the CL create buffer. And in OpenCL, all the device memory device memory are managed as buffers of the host memory. So that's why we will call them buffers. And for this function is essentially equivalent to the CUDA malloc. And this function will allocate object in the device global memory. It returns a pointer to the object for us to use in the future, and it requires 5 parameters. And we need to give it the OpenCL context pointer. You have already seen that context pointer. You need to have flags for access type by the device, whether it's read-only, read-write access, and so on. We'll see examples of that. And we need to specify the size of allocated object in terms of bytes, just like the other memory allocation in C. And then a host memory pointer. If we want to also have the runtime to copy the a host object into this newly created device memory object. So if we give a pointer for this parameter, it will not only allocate memory in the device, but it also will take a host object and copy that host object into the device memory. And of course, it will return an error code that you should check in all the real in your real programming exercises. So in order to free a device memory location, we can use CL release mem object. So this is equivalent to CUDA free, and this will free the object. So it takes a parameter which is a pointer to the freed object. So here we show a simple example of OpenCL device memory allocation. Assume that we want to allocate 1,024 single precision floating point array elements, and we want to attach the allocated storage to a pointer to the device memory called D_A, and we also use D_ to indicate that it's a device data structure. So here we show, we say, okay, we have a vector size of 1,024, and we declare a device pointer type, and this is important. You need to use CL_mem to declare any pointer that you want to be able to point into the device memory. And then we calculate the size. The size is going to be the number of elements in the vector times the size of each element, because we need to have the size in terms of bytes. So now we're ready to create a buffer, and we would remember all these memory allocation will be done to the context. So to the context. So if there are multiple devices, as we mentioned before, we will be actually creating one data buffer in each of these device global memories. So here we create buffer, and then we tell this runtime that this buffer will only be read by the by the device or by the kernel code. It will not be written by the kernel code. And we specify the size. We give two null pointers, and one of the null pointers here should be error, the error code. So I'm using a null pointer here for simplicity, but in your own code you should be checking error. And then there's OpenCL. After all kernel invocation and so on, after we're done, then we can use CL release mem object, and we give the D_A pointer to that API call to free the memory. So this picture shows an overview of how we're going to be able to execute memory copies and kernel launches and so on, in order to perform the equivalent of what we have been doing in CUDA until now. So each application is going to be issuing commands into command queues that were associated with individual CUDA OpenCL devices. So here we show a OpenCL context that has two OpenCL devices. And we just showed how you can create a command queue for one of the devices. You can definitely create another command queue for the other device. And then you can just issue the memory copy and the kernel launch kind of commands into the command queue for a particular OpenCL device. So this finishes the first part, or completes the first part of the OpenCL host code. So if you're interested in understanding more about the OpenCL host code, in addition to the OpenCL programming guide, I also like to encourage you to read sections 14.4 and 14.5 of the textbook. Thank you.